Hi, everybody. Hopefully you can hear me. I think I'm unmuted now. So welcome. Welcome to this fifth or sixth, somebody will tell me in a minute, of this webinar series. Apologies that we had to reschedule this one from the date that we had in December, circumstances beyond our control and so on. But we hope that we're now back on a groove and we'll be running these once a month. So hopefully you saw on the splash screen as you came in, that there are two ways you can contact us. You can use the chat box. So if you want to say hello, or if there's any issues with the sound or the video and so on, please use the chat. Or if you have any specific questions, please put those into the Q&A. What we will do is we'll try and make sure that we answer all of those questions today. If we don't do it as we're going along, we'll come back at the end and do that, but we will try and do all of those. So I suppose we should introduce ourselves again. My name's Derek Davis. I'm the Science Technology Platform Training Lead at the Francis Crick Institute here in London. And my colleagues in New York, let me hand you over to Kathy.
Thank you so much, Derek, and welcome everybody. My name is Kathy Daniels, and I am the Flow Cytometry Core Facility Manager here at Memorial Sloan Kettering Cancer Center in New York City, New York. And I will pass it along to Rui.
Thank you, Kathy. So yeah, my name is Rui Gardner. I'm the director of the Flow Cytometry Core Facility at Memorial Sloan Kettering Cancer Center in New York. And I have the pleasure of talking to you about today, again, about full spectrum flow cytometry, and where we will be covering a couple of important topics, essentially looking at the particular features of full spectrum flow cytometry compared to classical flow cytometry. So in particular, how can we take advantage of this technology to look at fluorochromes that have very similar or overlapping spectra? And also, how can we use autofluorescence in our advantage? Okay, so we will be taking a look at those things with Kathy on the instrument. Sorry, but for now, let me just give you a very brief introduction on these topics before we go there. So I just want to do a very brief overview. We did cover this in the last session, but this was almost 2 months ago. And so let me just go back and give you an idea of a very short idea of what are the differences between classical and full spectrum flow cytometry. So again, classical flow cytometry, the way we come about it is by essentially assigning one detector or one fluorochrome per detector, right? So for instance, if we have 3 fluorochromes, FITC, P, and APC, we would assign 3 detectors, one for FITC, one for P, and one for APC. And so essentially, one of the important things to understand is that, classical flow cytometry is spectral. Actually, all flow cytometry is spectral. And the big difference between this approach is that, and full spectrum, is that here we're looking at just a small window of each emission spectrum for each fluorochrome. And with full spectrum flow cytometry, what we're doing, as the name indicates, is that we're using all of the available detectors to be able to measure as much as possible the full spectrum of each fluorochrome. So we no longer assign one fluorochrome per detector. We are going to assign all detectors to all fluorochromes, right? And this will give us more information, hopefully, that enables us to not only do the same that we would do with classical flow cytometry, and here on purpose, we left the 3 filters that were used in classical flow cytometry and just adding all the other detectors. This is not necessarily the case, but this is just to illustrate that, at worst case, full spectrum flow cytometry is as good as classical flow cytometry. However, with the added information, we can hopefully be able to distinguish between fluorochromes that are actually very close. And this is the case of GFP and FITC, for instance. This is a classical example, I would say, already in full spectrum flow cytometry, where you can see that although in classical flow cytometry using the, let me see if, no, I was trying to get the pointer here. Is it like this? Yeah, there we go. So you can see that, for instance, using this channel, right, this filter for that we would use in classical flow cytometry, it would be very hard to distinguish between these two fluorochromes simply because they're green fluorochromes, right? They're most of their emission will be in this range. Now, looking at all of the detectors that are possible to measure FITC and GFP, you can see that their spectra are actually slightly shifted, and that can be enough information for full spectrum flow cytometry to be able to distinguish between these two. And I really like to use these images as example because you know, seeing is believing, and this is really striking. For instance, this you know, this image here where we have GFP being expressed fused with histone 2b, and then the actin filaments were labeled with FITC, right? So two green fluorochromes, it would be very hard to distinguish between both of them. And using full spectrum imaging, basically when you run the unmixing, this is what you see. So now you can clearly distinguish between what is GFP and what is FITC, right? So quite impressive, the capabilities that this technology has. Now, one of the very important things, and so we didn't address this in detail last time, one of the most important things when you start thinking of panel design in full spectrum flow cytometry is, okay, so you're telling me that it is easier to build a panel, but what are the rules that we need to follow, right? Now that we're looking at the full spectrum. And this is one of the reasons why I think it's very important not to call this technology spectral, because again, as I mentioned, all flow cytometry is spectral, and which means that the rules of panel design are still the same, right? We still follow the same, you know, because you could be confused by thinking that, okay, now we have a technology that's spectral, so perhaps the rules and perhaps the way we approach this new technology is different. But again, when it comes to panel design, etc., all the rules are exactly the same. So these are some of the rules that we have to address when we're thinking of panel design. Now, the important thing is with full spectrum flow cytometry, since we have more information from the fluorochromes, like I said, worst case scenario, we're in the same conditions as classical flow cytometry, but in the best conditions, we can actually go a bit further. And here are just two examples that from a slide that I borrowed from Monica Delay, which I acknowledge and thank her for allowing us to use these slides. You can see, for instance, an example here where we have APC versus Alexa Fluor 647. Again, two very overlapping dyes. We would never use them in classical flow cytometry. It would be impossible to distinguish between both. But the fact that their spectra is slightly different in a few channels allows this technology to be able to distinguish and pull them apart. And so we can use them. And as you can see, we have clearly a population that's positive for Alexa 647 and a population that is positive for APC. And the same thing goes for BV421 versus the super bright 436, right? Where there's only a portion here where the signature is slightly different, and that is enough information to be able to pull apart. And you can see two distinct populations expressing the marker that's conjugated to, or that's identified by the antibody conjugated to BV421 and super bright 436. Now, are we saying that this is a smart approach to use fluorochromes that are so overlapping? Of course not, right? And I think this is an important message here, is that we're not trying to say that, oh great, now we have these capabilities, we're going to start using all these overlapping dyes. No, of course, like I said, we still follow the same rules, and the best practices in panel design are to use fluorochromes that are as separate as possible in their, wavelength. But of course, as you start adding, as you have 20, 30 markers altogether, it's difficult to find 30 fluorochromes that completely separate. So the fact that this technology allows us to, and still can distinguish between two fluorochromes that are very overlapping is actually quite interesting and quite beneficial, because it allows us to build those panels. Not only it allows us to build those panels, but maybe in an even easier way. So I should put it this way: it's much more forgiving when it comes to building panels that have overlapping dyes. Coming back to the example of GFP and FITSI, I just want to show you some of the tools that Cytek has on their website. So we would encourage you to take a look at the Cytek Full Spectrum Viewer. This allows you to overlap all of the dyes that you want to use and try to understand if, in fact, this technology and this instrument in particular is able to pull these fluorochromes apart. Of course, you never know until you try it, because it depends on many other factors, not only their spectra and how much they overlap, but definitely this is one of the most important things. So looking at the spectra viewer from Cytek, you can see that EGFP and FITSI are slightly separated or shifted, but the thing is, how much do they have to be shifted for us to know if they're going to work together or not? So Cytek did introduce an interesting metric, or a couple of metrics. One of them is the similarity index. And the similarity index scales from 0 to 1, where 0 is two completely distinguished pairs of fluorochromes, and 1 would be they're completely overlapping, right? So we can see here that GFP and FITSI have a similarity index of 0.93, so very close to 1 as expected. And this is already indicating to us that this probably wouldn't be a very good choice to use these two fluorochromes together. But when it comes to the whole panel, there's another metric that Cytek introduced, which is the complexity index. Of course, here the panel is just two colors, right? That we're showing here. So not a very complex panel. But if you read the description of what the complexity index means, you'll see that for 10 dyes or fewer, a good panel would have complexity indices around 2 and 3. And with just two colors, we already have a complexity index of 5.25, which would be relatively high. And again, it's already indicating to us that this wouldn't be a very good choice to use. But again, there may be circumstances where you only have a certain antibody conjugated to FITSI. You can only access the cell line expressing GFP. So there may be conditions in your experiment that you would either have to change your panel design, or even change your experimental design to be able to use other dyes. If you can actually use them together, this is really amazing. And this is exactly what Kathy will show today in our first experiment, where she will be showing us two very overlapping dyes and how we can still resolve populations. So I'll pass it to you, Kathy.
Okay, thank you so much, Rui. So I'm going to go ahead and get started on the Aurora. Okay, I'm going to go ahead and share the screen here. All right, so I'm going to go ahead and get started with a run like Rui spoke about, where we're taking a look at two fluorochromes that are traditionally very similar, okay? So the first thing I'm actually going to do is I'm going to open up the spectrum viewer that Rui just spoke about by opening up Chrome. And that is the suggested viewer to look at, because I want to get an idea, if I'm trying to take a look at two fluorochromes that are similar, what is the similarity metric that Cytek has put together for these two different fluorochromes. So if I go to spectrum.cytekbio.com, The two different fluorochromes that we're going to work with today are PAC Blue and BB421 for the start of our experiment, okay? So you see right now, someone else has previously used this at the instrument. So I'm going to X out of that fluorochrome, which is AmCyan, and we have a blank slate to work with. Okay? It's important when you go to use the spectrum, full spectrum viewer from Cytek that you choose the appropriate configuration for your instrument. So we're working with a 5 laser Aurora unit today. So I make sure that that configuration is chosen. And I'm going to start searching for those two fluorochromes. So PAC Blue is my first fluorochrome that I'm going to be using today. And by double clicking on it, we see the emission spectra on this full spectrum plot. From there, we're going to add in BB421. So I start typing in 421, it pops up, and I double click on that fluorochrome right here. Once that pops up, you can see that we do have 2 distinct emission spectra. So this might be something where you look at it visually and you say, oh, I think there's a good chance that we are able to pull out these 2 fluorochromes from each other. Okay. Jim, I did just see that. Hopefully you get a little bit of a better visualization here. And let me make that a little bit bigger for everybody as well. Okay. Now, the next thing that we want to try and do here is we want to try and see what the similarity matrix is for these 2 fluorochromes. In order to do that, you can see where my mouse is hovering. If I click on similarity and complexity, this is a graph that's very, essentially what Rui was showing us in the slides here. And it's telling us that the similarity index between BB421 and PAC Blue is 0.78, okay? The closer those values are to 1, the closer they are to being exactly similar, right, or identical. So we're gonna go back to the instrument now and try a run with mutually exclusive markers, CD4 and CD8 for BB421 and PAC Blue.
Kathy, can I just ask a question? At that point, obviously we're using the Cytek Aurora because that's what you have in the lab, and we're using their full spectral viewer. Do other companies have something similar to that, that spectral viewer?
Oh, to the spectral viewer, yes. There are other spectral viewers available. So if you just simply Google fluorescent spectral viewer in Google, there are a couple of different varieties that pop up from different vendors, and there's also one of my favorites that pops up for fluorescent proteins, since we see a lot of different fluorescent proteins that pop up, which is fpbase.org. So they have one. There are ones from BioLegend, Thermo, BD, across the board. But specifically when talking about this similarity and complexity index for full spectrum flow cytometry on the Aurora units, that's where this one comes in handy.
I suppose with the traditional spectral viewers that you'd get from the bigger companies, they're really, you change the laser, don't you? And you look at the emission for that wavelength, whereas this is slightly different.
Exactly.
You're actually getting the whole spectrum in one graph, if you like.
Exactly. Yep. And there are other options out there. So I believe there might be spectral or fluorescent spectra viewers that mimic full spectrum by different vendors, specifically BioLegend, I believe, and I think someone just commented that also. But as far as the complexity and the similarity, I don't believe they have that, but I can be corrected if I'm wrong because I'm not certain.
I probably should know this myself, but I wonder whether microscopy companies would have something similar.
Potentially, yeah, potentially. Thank you, Derek.
Okay. Can I just sorry? Can I just comment something there also? So the big difference between this spectra viewer and most other spectra viewers is that it's displaying the intensity for the channels, and that's why you were mentioning, Kathy, right, that it's important for us to specify what's the configuration. Yep. So this spectra viewer is actually mimicking the detectors or the channels that the Aurora has, right? Whereas you could go to BD or Thermo Fisher or BioLegend and just ask to display the signature, right? The spectra and see how much they overlap.
Yeah, right. So if we change this configuration, right, it absolutely will change based on the excitation sources that you have on the unit, right? So for example, if we change it here to a 4 laser, this is going to look a little bit different. And if we
Right.
click on the similarity, I believe that value might potentially be slightly different as well, based on the lasers that we have on the unit itself.
Mm-hmm. Right.
Yeah.
So it's tailored for the Aurora. Right.
Yes. Mm-hmm. Yep. Okay. So what we're going to do now, as long as we have no more questions, is we're going to go ahead and we're going to actually focus on the run in the Aurora, or in the spectral flow software itself, utilizing the Aurora. So I'm going to minimize the spectral full spectrum viewer. And what we see here is the home screen for spectral flow. Okay. I am signed in as an admin. So for some people who are utilizing the Aurora, they might not see all of these options. But what you will see, no matter what, is this acquisition option right here. So we're going to go ahead and get started. And once I click on acquisition, what I'm going to do is I'm going to get started with a new experiment, okay? Once I select a new experiment, it's going to let me put in all of my experimental details. So I'm simply going to name this CD4, CD4, CD8 test, OpenFlow. Okay. Now here in the library, we can choose which fluorochromes we're using for our experiment. So as we just discussed, we're going to be using PAC Blue and BV421. Helpful hint, if you type in BV, all of the brilliant dyes are going to pop up and you might have more to search from. If you type in 421, it'll be right there, okay? So I'm going to go ahead and double click on that to add the fluorescent tag. And I like that we can do a quick quality check to make sure that all of our fluorochromes have been added, because it gives you the number, the cumulative number right there. Okay. Go ahead and go to next. And again, some of this is a review from our previous session, which you can find on our YouTube channel, which is OpenFlow Cytometry. But what we're going to do here first is we're going to add our reference group. Okay. This is going to be where we're able to define our unstained control and also our single color controls, which are reference controls. Okay. No matter what, we always need to make sure we run an unstained sample that is the same cell type as our experimental samples. So we have these unstained cells right here. And then under fluorescent tags, we see that we have the option to choose between cells and beads. Okay. So our single colors today are for cells, or are with cells. And one thing that I prefer doing for the negative control, we have the option in spectral flow to set a negative gate as we're doing our unmixing to reference the negative population. But whenever I'm staining cells, so long as my unstained control is the same cell type, I would prefer to have this unstained sample as my negative control, because if you have an oversaturation of your antibody and you have your negative cells shifting up, whether it's with viability dye or antibody, it's no longer a true negative or a true unstained if you have background fluorescence. So that's my preference, okay? It's essentially just telling the instrument and the software, this sample right here is our negative for all of these, okay? So then I'm gonna go ahead and select save here to save that reference group. And you can see there's a little R next to each tube indicating that those are our reference group samples. Now I'm going to add another group, and this is going to be for my fully stained sample. You can name it whatever you like by double clicking. And if you had a variety and much more, or many more than one, or more than one sample rather for your experiment or for this group, you could always type in a specific number of tubes before you make the group and it'll add that number, okay? But for this, we're good to go ahead. So I'm gonna go ahead and select.
Kathy.
Yes.
Sorry, before you go ahead, there was a question about the negative, so the unstained control. Mm-hmm. So someone was asking, you know, if that unstained in the reference group is the same as the universal negative in DIVA.
So I would say it's similar, but a little bit different, right? So we have, if you select that negative or unstained population for all of those, it does become essentially like the universal negative. But in addition, the spectral flow software, and Rui, feel free to chime in here and give a little bit of a deeper explanation, but we need that unstained cell control in order to accurately calculate the unmixing, because it actually uses the autofluorescence of those cells in order to do the unmixing.
Exactly, exactly. That's a very important distinction between, you know, when we're looking at DIVA, we are not, you know, we're essentially using the universal negative or the unstained for compensation, right? Here we need that for unmixing, and I'll mention that in a moment when we talk about autofluorescence. But for unmixing, we also need to take into account the signature of the autofluorescence as, you know, as an extra fluorochrome. So that's the biggest difference here when we're dealing with unstains. And we did go through this in the last session, right? That's being recorded.
I think that might, there's a question that's also appeared in here that might be relevant at this point, is the pros and cons of what we use as our single color control, whether it's cells or beads, because obviously, yes, the fluorochrome we're going to look at the spectrum of the fluorochrome, but what influence is the carrier going to have on that?
Right. Yeah. You want to answer, Candy?
Sure. It's a complicated question, I think, with a complicated answer.
That's what we want, right?
Yeah, exactly. So there are many instances where we will use beads on the instrument and it works perfectly fine, right? So these FC capture beads that are typically used are really, really nice in case you have a rare cell population, something that's expressed at very low levels, precious sample that you can't really sacrifice. These are all circumstances that will lead you to use beads. There are certain types of beads that might not play very well with certain fluorochromes, right? So you have to be very careful sometimes. So the best suggestion that I personally would make and want to make is to try beads and cells, right? For the first run of an experiment or a panel that you're trying to design, and see what works best, right? Because a lot of times beads will work perfectly fine and there's no issue. You might once in a while run into something where you see that you're unmixing or compensation, because it's not just on full spectrum units, it's on conventional cytometers as well, where the results don't look as expected. So I would suggest bringing both and make sure it works, and then go back and continue on with your experiment like that.
Yeah, that's very important. Let me just add that, you know, again, the rules for a good composition control are the same rules for a good unmixing control. So everything is exactly the same as it was for classical flow cytometry. But I do want to bring up something that maybe is becoming somewhat of a misconception regarding this new technology, which is the fact that some people were not used to using best practices, so they weren't following exactly these rules of a good single stain control. And but in this case, since we're just looking at the small window, so for classical flow cytometry, we're just looking at a small window. Sometimes the fact that you know, people weren't following the rules, like not bringing exactly the same fluorochrome, these differences weren't necessarily within that range. They were more in you know, outside of that. And so when it came to compensation, things kind of worked, right? And then there's another thing that people tweak compensations afterwards, but we won't go into that in detail. But assuming that, you know, the differences are not that big, then, you know, things kind of worked. The issue here is now with a technology like this, where you look at all the full spectrum, and this is the brilliance of the interesting part of this technology, is that you can really distinguish between two very similar fluorochromes. But on the other hand, then if you don't really apply best practices, you're going to run into two problems, right? So if you use a slightly different fluorochrome, this technology can distinguish between that control and the sample as being two different fluorochromes. So the bottom line here is that we really need to be careful with the controls we're using. It's not that in full spectrum you should apply best practices. You should apply best practices always, but this technology is more sensitive to pick up problems when you don't apply best practices. So just be aware of that.
Yeah, and actually, there's another question that sort of fits along with this, because we're using our single color controls here. We saw last time how you can have a reference library for these things. So do we use that all the time? Do we bring single color controls every time, as we would probably recommend for flow?
Yeah.
Traditional
so typically,
flow.
Yeah, I mean, typically in our lab, what we suggest users to do is to bring the controls each time. So there are options in the software to have a reference library, but you know, to account for differences in reagent and the reagents from day to day, especially tandems, we do suggest for people to bring their controls every time. So that's our personal approach in this lab. If that's a comprehensive enough answer. Any more? Oh, sorry, go ahead, Ray.
Yeah, I think there's another question here from Cedric, and this has to do with you know, what were you talking about, the similarity index. Cedric is saying that that he's having a hard time with the meaning of 0.78 on a full signature profile versus 80% compensation between two colors. You know, and then he goes, so I can read the whole question. It's all about the calculation of an algorithm between signatures. For two close colors, CD4 and CD8, for example, it was already working in classical flow cytometry. It was already easy to distinguish. How to set the limits? Some say the complexity index should be above a number like 0.6 or so. What do you think? You know, I can start by answering this, and if you guys want to chime in also. Yeah, no, these are two completely different metrics. So 0.78. So again, compensation or spillover values are not limited between 1 and 100, right? Or 0 and 1, I should say. Whereas the similarity index is a metric that's that goes from 0 to 1. So these are two completely different metrics. So a 0.78 similarity index is has nothing to do with 78% spillover value. Two completely different things. In terms of the limits of you know, when you can use, so what is the value that you can be comfortable with? I actually forget what's the value that Cytek, and I know there are some Cytek people here watching this, and maybe they can chime in. I know that they recommend 0.99. Okay, so anything below 0.99, you can still use it. Thanks, Jim. So anything below, in principle, you can use. Now, the very important thing is that, again, there are other factors that come into play. It's not just the similarity index or how similar the fluorochromes are, right? And actually, Cedric was mentioning, if they're exclusive, right? And we're going to talk about that, right? If they're co-expressed, then even with full spectrum flow cytometry, you may have a huge difficulty. Having said that, I don't think that if you used CD4 APC and CD8 Alexa 647, that, you know, in a classical flow cytometer, that things would work very well. So, you know, but it is an important thing that we're going to stress here, that things may work if they're exclusively expressed, mutually exclusive, but if they're co-expressed, you may not be able to distinguish them also.
I also suppose conceptually you have to think, you know, if you were to try to run APC and Alexa 647 on a classical flow cytometer, you can't do it anyway unless you change the filter setup and look at one part, one area and one part in another. So
right.
There are some conceptual differences, aren't there, that we have to get used to, I think.
Yes, 100%. And it's also important to note, and I think this has been said a couple of times, so I just want to stress the importance that this isn't like a carte blanche, right? You can't just say, all right, I can pull these apart to get these two different fluorochromes, right? Or where we do have this full spectrum capability, so I can put whatever fluorochromes I want together in a panel. We still need to make sure that we take into account all of the appropriate considerations when we're talking about panel design, talking about level of expression, co-expression, spread, all of that. We still see that on these units, and we need to take that into account.
Absolutely. I think we said last time, just because you can do it doesn't mean you should do it.
Right.
Exactly.
Right.
Exactly.
And again, the rules are the same. Right?
Okay, so I think we're good on questions, it seems, at this point. So what I'm going to do is I'm going to go ahead and go to our next step here. Okay. And actually, one quick thing that I just did want to reference back to for the original question when talking about the universal negative, it's important to remember that on, you know, a conventional unit, typically, like, for example, the Fortessa or even the Cytoflex or whatnot, you can run without an unstained control to carry out compensation. And you could just draw in the negative gate internally for each one. Here, we need to make sure that we have the unstained cells so that we take into account the autofluorescence. Okay. So I'm going to go ahead and I'm going to go to next. And here in this area of the experimental setup, what we can do is we can go ahead and set labels for each fluorochrome. So if I double click on the top here for the whole experiment, if I type in CD8, that is my BB421. It doesn't carry over to the reference group samples. I did have the option to label when I created the reference group, but I typically tend to skip that, okay? Now here for pack blue, I'm gonna type in CD4 and hit enter. You do also have a list of CD markers here that you can click and drag in, should you like. I typically just tend to go ahead and label it myself. Now, I'm gonna kind of skip through keywords. You do have the capability to add FCS-specific keywords to your files. I wanna stress that Cytek does have a YouTube channel where you can go and check out a lot of educational content they have for how to do things in SpectralFlow, and it's a really wonderful resource. So anything you might be interested in here that we're not going over, they do have there. So I'm going to go ahead and go to next. And here in our acquisition tab, what we see is the ability to set stopping gate, storage gate, how many events we want to record, so on and so forth. Okay. So what I'm going to do is I'm going to make sure that I record a minimum number of events from our raw worksheet. And what I like to do typically is make sure that I have a certain number of events recorded by scatter. So I know in our raw worksheet that P1 is equivalent to a debris exclusion or a scatter gate. So I'm going to select P1 here. Whenever we're doing our reference sample acquisition, we always work in the raw worksheet so we can see that full spectrum, right? And the full spectrum signature of our unstained and our single colors. I forego storage gate. If I have a storage gate selected, anything outside of that gate will not be recorded. There are only very special applications for that, and it's not something that's typically used very often. Here, for the amount of events I want to record, I'm going to go ahead and select 20,000. Okay, that number is going to change depending on, you know, if you're using beads or you're using cells and population expression to make sure you have enough positive events, right? Typically for unstained, I like to make sure that I record at least 20 or 30,000 or so. I'm going to not put anything in for time or volume. I have a good volume in my tubes and it should go pretty quickly, but that is something that you can adjust if you wanted to. At this point, I'm going to save and open this experiment, and it's going to go ahead and automatically open up this default raw worksheet for us here. I have automatically in this worksheet a scatter plot that has this P1 gate, like I mentioned before, which is debris exclusion. We typically have it set up where our second plot is our forward scatter height versus area. And then we have this full spectrum plot, which shows us all the detectors versus intensity. So you can think of it like many, many histograms, or all of the detectors as histograms on their side. That's a nice way to view. And then we also have all of the histograms here, okay? So again, we went over this during the introduction to the Cytek Aurora on our first session, where we went over all of the acquisition controls and all of the instrument controls. What I do want to reiterate from that first session is that it's very important to always start off your experiment using the Cytek assay settings, as these have been optimized to get the best settings for your instrument, okay? So I'm gonna go ahead and I'm going to vortex our unstained cells, because whenever we're starting off, we wanna make sure that our scatter is set up appropriately. So I'm removing the tube of water I have on the instrument and loading our unstained cells. I am going to leave the flow rate here at low. All right, I don't want to go ahead and blast through too much sample.
And Kathy, can I just ask a question for those who've not seen the machine? Is this a pressure?
Sure.
This is a pressurized system, rather
So
than just a syringe-based system.
So this utilizes Rui, correct? I'm going to have you come in here. I think there's
it's vacuum. It's vacuum based.
Yeah. Thank you. He has a little bit more information on it. All right. So then what we're going to do now is we're going to go ahead and select start. And when we select start, we're going to see our events popping up in just a little bit. It's important to note that unless you deselect it, it automatically takes up a starting boost sample to be able to go ahead and get the sample coming through pretty quickly. Now, what you see here is I have about 600 events per second that are coming through, but I'm not seeing what looks like cells on the plot. Now, the cells that we're working with today are very cell leukocytes, which should have a traditional lymphocyte, monocyte, and a small granulocyte population. And I'm not seeing that. So what I'm going to do is I'm going to go ahead and I'm going to make this P1 gate a bit bigger. And I'm going to try and show our population hierarchy here. If I click on the population hierarchy and I click and drag, this P1 has 2%. If I drag it to the edge of the axis right here, 45% of our events are off scale. Typically, when you start off, you're going to need to reduce your forward scatter gain, okay? So if I change this gain to 100 and hit enter, what you can see is I see a lot more events now that are on scale for forward and side scatter. Okay.
So I suppose, Kathy, that's very similar to what we looked at when we were doing the Diva. And
exactly.
when we set the machine up with beads, the voltage is way too high for what we'd expect with cells.
100%. Yeah, there's going to be a very big difference between beads versus cells. And that's why using the gating and using the population hierarchy can be really helpful for us in order to understand where our cells lie. But definitely. Okay. So then you'll also see that even though I have most of my cells on scale, it's still a little bit high. So I'm going to reduce this forward scatter and bring it down to maybe about 75. And when I restart here in the acquisition control, what we see is if I bring this P1 gate to the axis, I have less than 1% that's off scale. But what I do still see is that I only have 70% in this P1 gate. You do have quite a bit in the way of background and what events that we want to threshold out. So what I'm going to do is I'm going to go ahead and go to this threshold tab. And each small tick here before 1 million is 200,000. So I typically tend to use that to help me decide what I want the threshold to be. So I'm going to set that at 200,000 and hit enter. And when I restart, what you see is any of the events below that first tick are no longer showing up because we've thresholded them out, okay? So now we have close to 90% in that P1 gate. I'm going to go back to the gain, and I'm just going to make the side scatter a hair higher. So I'm going to try 130 and restart. And I think this should be okay for our purposes today.
Sorry, Kathy, Jim was just asking another question there about do we typically need to change those voltages for most cells because the beads are pushing everything up off scale? So that would be the same for virtually any cell type.
Yes, I have never run into a circumstance where I have not had to change that forward scatter gain. So sometimes the side scatter will kind of be close to where it needs to be, but for forward scatter, I would say 100% of the time I've had to reduce it. You might even, there has been updated hardware on the instrument. Some people might run into the circumstance where they're working with very large cells that even going to very low forward scatter gains, the signal might still be off scale. I think that hardware change is going into effect on most instruments, likely if it hasn't been done already in the near future. But what you're going to want to keep in mind is that you do have the ability to change forward scatter area scaling factor, which we did go over in our last session, I believe, but you do have the ability under the lasers tab to adjust the forward scatter area scaling factor if you have the permissions, okay? Now that I have the cells on scale, you see that I don't really see many events, and part of that is because the events to display is only 2,000. So you do have the option to change how many events are showing up on your plot. But I don't want to run through too many of my unstained because I still need to record them. But before I record, I want to stop because I need to take a look at our fully stained cells to make sure that they are on scale by fluorescence. So we've checked our forward and side scatter, we've checked our threshold, and our next step is to make sure with our fully stained samples that none of the gains need to be reduced. Okay. We did talk about this last time, but it's very important to stress that we are looking at the full spectrum, right? So I'm gonna actually close this out for now, and I'm gonna bring this a little bit further. Actually, let me come over here. When we're looking at this full spectrum plot, if I put a sample on and you had a signal that was off scale, off of a certain laser line, I want to stress the importance that what you never want to do on these units is you never want to change individual gains unless you've had a conversation with someone from Cytek and there are special applications for this, so that, you know, anything I'm saying, if you speak to someone from the company and there are specific applications, like I said, listen to your representative. But for most cases, if you have signal that's off scale, say for DAPI, that's a culprit that comes up quite often. People stain their cells for viability with DAPI, and they're very, very bright off the UV and the violet. You wouldn't want to make changes to individual detectors and bring them down, but rather what you would do is choose the appropriate laser and reduce the gain by a certain amount for all of the detectors off of that laser line, okay? What that does is that preserves the spectral signature and brings it down as a whole, as opposed to changing the spectral signature to bring down the individual detectors, okay? So I'm gonna put on our fully stained sample that has PAC blue and BB421, okay? Notice that I'm still working from the reference group. I'm not recording anything just yet. All I want to do is run this fully stained to make sure that everything is on scale. And I am going to look here in this P1, in this full spectrum plot for that. Okay. So when I put this on, what I do see is I do have signal that's popping up, okay? I can focus in on my lymphocytes if I want, okay? Because I do expect to have the CD4 and CD8 population right here, and nothing is off scale. So I do not need to change any of these settings as far as the gains go for fluorescence. So I'm gonna hit stop, and I'm at the point now because I've adjusted my scatter settings, my fluorescence is all okay, and my threshold is good. I'm gonna go ahead and record all of my reference group samples. So I'm putting my unstained back on. I'm going to change the flow rate to go a little bit higher, okay? I'm gonna go ahead and select start. Some people might ask the question, how fast can you go, right? So some people might say, oh, I've seen that you can run them at up to 30,000 events per second. I want you to be mindful that as you're running, you want to take a look at the abort rate to make sure it's not too high, right? So you don't want to blast them through too high. I'm still going under 1,000 events per second, so I'm going to change it to high. These are lyophilized cells that aren't too concentrated. And I'm going to go ahead and hit record. Okay. I might not have 20,000. I'm going to do our best to see how many we have here. We do have good number of cells though. And I did adjust my P1 to focus on these lymphocytes, which is my population of interest here for this experiment, seeing as how we're working with CD4 and CD8, okay? I do know that the monocytes, we do expect some level of CD4 staining there. but our population of interest today is the lymphocytes.
So Kathy, that abort rate, is that the actual cell number or is it percentage? Another question here from Jim.
That's the cell number.
Okay.
Yeah.
So we'd have the same considerations as again, as a conventional flow cytometer here about the pressure that we apply. We don't want to go too fast because we'll see more spread of the data.
Yeah, exactly. So ideally what I would like to do, right, is to concentrate these cells and run it at a lower flow rate. I'm working with lyophilized cells that aren't too concentrated and working with small numbers of cells. So I kind of had to work with what I had, especially taking into account that I wanted volumes that we could talk through things and I could yammer on and on and on talking about these different principles. So I didn't concentrate them up as much as they could have been. Now this is about to run dry. So I'm going to go ahead and select stop. It's perfectly fine that I didn't get to that 20,000. I have more than enough cells here in order to successfully unmix. But I didn't want to risk.
Is there a minimum number for that?
So when we're talking about positives, I like to make sure that if you're talking about a positive population for, say, for BB421 or PAC blue, my aim is at the very least 1,000. For unstained, I don't know the specific number by Cytek that they define for the spectral flow software. So if anyone's online that has that number, but if you have 10,000, it works, that's perfectly fine. 5,000, it works. I typically like to have 20,000 unstained, but also remember that for your unstained sample, if you're going ahead and comparing that and using it for gating, you want a nice robust population. So I would say more isn't a bad thing, and it's always better.
Yeah, so Jim has put in the Q&A that 400 was recommended. I think he's just been on the training course. So
for the positive, probably.
For the positive, yes.
Exactly. Yeah. I think, you know, for me personally, the CV of the data goes down a little bit when you have 1,000. I've always looked at that when you have a rare population of interest. I try and get to at least 1,000. That's my preferred number, but 400 does work. So I went ahead and I vortexed the BV421. I'm leaving it at high because these are all the same concentration. I'm selecting start. And then once I see these events pop up, I'm going to go ahead and record.
So do you set, as another question, sorry, Kathy, do you set a volume to aspirate when you start this?
That is in the initial settings. So if we went back to edit and we were looking at the original experimental setup, you do have the option to stop at a certain volume or a certain time. I have about 300 microliters in here. So I could have theoretically said I want to stop at, you know, maybe 150, give myself a little bit of extra volume just in case. I prefer to use that when I'm working with plate mode. If there's a certain volume I want to work with, I don't typically tend to do the volume stopping for tube, but that's personal preference, but you absolutely can. Now here, what's going to be something important that we do is we want to reference another document in order to check the spectral signature. So you always want to go ahead and QC your experiment as you're going through to make sure that your reference controls, your single color controls, look as they should. So we see this full spectrum plot and you do see a difference from the unstained, and that's your BV421. But here it's showing me all of P1. So what we can do, we have two options here. If I want to see specifically the BV421 signature to check it, what I can do is I can right click on this axis here on the second plot, and I can choose one of the detectors that I know has BV421, right? So, or is going to show that signal. So it's brightest around V1, V2. So if I click on that, what we're able to see here is we're able to see the BV421 positive. If I then click on a gate here, I can go ahead and choose our 421 positive. And then if I click on the full spectrum plot, what I do have the capability of doing is changing the plot gate. So I'm visualizing P2, and this will show me that signature. Now, one thing I probably should have done before that, so it's nice that you get to see my mistake, is I probably should have gated this plot based on P1 before I did that. So let me go ahead and fix that. So I'm going to show the population hierarchy to show the mistake. that I made. So I set P1 to independent of P1. What I can do is I can delete that gate. I can go to the plot properties, change that to P1, and then I can set the gate so that it's a child of P1. You also have abilities to kind of move this around here in the software. I just wanted to show you that approach. Now here, as opposed to all events, if I choose P2, we can see the signature of BB421. Okay. Now, there's a document that's going to be available by Cytek. They have it on their website. And we always train people here in this facility as you're running your single colors to check this. So if you hit Control F, what you can do is you can search for that fluorochrome, right? And then you can see BB421 pops up. It's going to be very small on your computer, so I'm going to make this as large as I can for everybody. But what we see is with the known fluorescent signature of BB421. So if I click on it in the software and then I open it up here, what we should see is that these signatures should match up. We have a bit of excitation off of the UV, namely around UV 3, 4, 5, 6, and it tails off, which is what we're seeing here in the software, and then the same off the violet, okay? So I did check these at another instrument earlier, and I'm not gonna go over the pack blue, but these had been checked earlier to make sure the signatures did match up. I just wanted to reiterate that that is something very important to do. Okay. Select pack blue, go ahead and start that sample, and then we're gonna record so that we can go ahead and get started with our unmixing to see how these results look. Okay. There it is. I'm going to go ahead and select record. Now you're going to notice I don't see anything on this full spectrum plot anymore. That's because it's gated on P2 and there's nothing in this P2 gate. If I shift this over, what you now see is the pack blue signature. And you'll see that it's actually much brighter on V3 than it is on V1, which is why this has shifted down so much, okay? Now, if I did, I'm gonna go back on my Word. We will go ahead and check it out. So we do have the time as it's recording. So let me type it in again. If we scroll through, I'm gonna see if I can find this. Positive pack blue right here. So if you see where my mouse is hovering, we have a little bit off the UV, and then you see V3 right here. It's the brightest, and then it tails off, and it shows a little bit off of the blue. And that's exactly what we're seeing right here.
So Kathy, sorry, can I interrupt you? There's another question from Cedric here about looking at the full signature. So can you from that tell if the staining is bad? You know, and if you can, how does that manifest itself?
So I think oftentimes what you can tell is if you've had a swap of tubes, right? If you haven't stained, if you see that the signature is drastically different, there might be some issue with tandem degradation. You might have some issue with the tubes being swapped. You might have run into to something at the bench, and that's if something looks completely off. If you put a fully stained sample on and you look at it with the raw full spectral plot, it's going to be very hard to identify if something's off, right? Because you don't have the unmixed data. So that will be very difficult to do, at least for my eyes. I don't know. I wouldn't be able to look at that.
So really, it's a check that you put the right tube on.
Exactly, and to make sure there's no degradation of the dyes or anything like that.
So you'd see that, would you, on that plot? I suppose particularly if it was a tandem dye.
Yes, for tandems, you might be able to start getting an eye for what that looks like. Also, I can say very honestly, if I'm training someone and we're supposed to be using, you know, one fluorochrome and they bring me another one and they don't follow that rule of compensation on mixing, I say, oh, you didn't bring that one, did you? And I was like, well, I had another antibody. So it's something that you get used to these spectral signatures, and you can pick that out pretty easily.
So let me just add there. So I think Cedric is also mentioning the fact that If it's too, so if each channel is too diffused, so if you're seeing still a lot of the unstained, right, or the autofluorescence together with the signal, that may be an indication that the staining is not very good. And that could be a way, I mean, you could do what Kathy is doing, which is look at the main, you know, the highest channel, right? In this case, the V1, where you can see the quality of the staining, or you in the full spectrum. Yeah, exactly. Like Kathy is showing now. If it's too diffused, yeah, that may be an indication that the staining, I mean, it doesn't mean the staining is bad. It's just may not be as good as you would expect, right?
Yeah, exactly. And if you're using, yeah, and if you're using cells as single color controls, and we go back to that question about how many is enough, right? If you have a gated population and you look at the detector where the signal should be the brightest, what you can do is you can go back and edit this experiment, go into acquisition, and with that gate that you just created, make sure that you're recording at least that minimum of 400 to 1,000 if it's something rare, so that you know that you have enough. And then when you go in to do the unmixing, you can set the gate with the understanding that you really know where that is based on the unstained, and you can kind of help yourself out there.
Yeah, there's a comment actually about the number there in the Q&A, and that you should get an error message if it's too low, maybe about below
it will.
200. So.
Yeah, it won't let you do the unmixing if you don't have enough events.
Yeah. And there's one more question. I know we'll have to move on because I'm conscious of the time as well.
Yeah.
But the pattern there is going to be similar if you were looking at another population, right? Because it's the fluorochrome that you're looking at there rather than the actual background cell.
Right.
So if your back blue B421 was on a neutrophil marker, for example, the pattern would be the same.
Yeah. So you can see if I kind of come up here and go down there, the signature, it still remains the same. It's just the different carrier particle. So we're looking specifically at the fluorochrome itself.
Yep.
Okay, great. So now that we've gone ahead and recorded these single colors for these two fluors that have a very similar spectral signature, what we're going to do is we're going to go ahead and unmix to see if it works. Okay. So we're going to click unmix. Let me go back and do that again in case I did it too quickly. So I'm hovering up here, right? And there's this unmix option. And if we click on that, we're just gonna, we're using our controls from our experiment and not from the library. We use them fresh, freshly made up. And here we see we have BB421 and PAC blue, okay? I know that some people might have questions on the autofluorescence. That will be coming shortly. So we're gonna go ahead and hit next, but we're not gonna focus on the autofluorescence right now. Here, remember from last time, what we can do, if I click on control on our keyboard and I make changes to our scatter plot, our P1, it's gonna change for all the cellular controls here, okay? So as I make that change, it's gonna apply to all. Now again, I'm focusing on this population because all I'm looking to analyze today is the lymphocytes. Okay? I am ignoring this negative gate because I reference the unstained control as the negative here. So I'm not going to focus on this negative right here. And all I'm going to focus on is making sure that my positive gate is in the right position, okay? We make sure it's around the brightest part of the positive. If I were to set this positive gate here, I would have errors in my data. It would not look good when we looked at the data, okay? I need to make sure that our positive is around the brightest part. Again, single color controls need to be as bright or brighter than the experimental sample. So we're following that rule, okay? Now, once these gates are set up appropriately, which they are, I'm going to choose live unmixing in the bottom right. If I were to choose unmix, save, and open, it would unmix all of the data that I currently have recorded and open up a new experiment. And I still have a sample to run. And I want to see what it looks like unmixed live. So I'm going to select that option. Then when I go, I'm ready to run our fully stained sample now that the unmixing is done. And if I click on that, what you can see is it automatically is still going to our default raw worksheet. So I do have the capabilities to edit my experiment, go to acquisition, and I can change it so that my fully unstained is going to be in my unmixed worksheet. And again, let me make sure from my scatter gate, I'm recording enough events. and I'm going to go for 20,000 again, okay? I do have the capability to toggle back and forth between worksheets, but I want it to automatically be set so that this is looking at my unmixed, okay? I'm going to take the fully stained sample and load it on and see what our CD4, CD8 combination looks like with PAC blue and BB421. So I have the cells that are just loaded up. I'm going to start recording as soon as I see it, and then we're going to set the gates as we're going. So I'm going to start recording. Okay. If I double click on this P1 gate, which is my scatter gate, we can then create our second gate and create a parental gating strategy. So if I right click, I can choose forward scatter height. And you see now, I'm no longer seeing UV 1, 2, 3, 4, 5, 6, so on and so forth. I'm seeing the parameters now that it's unmixed, which is what we're more traditionally used to seeing. I'm going to select a polygon and set a singlet gate and double click to close. Create a population hierarchy here, which already exists, so never mind. Come over here, double click here, and then what I'm going to look at is CD4 on the X, and on the right, we're looking at CD8, okay? So what we see here is we see that we have our CD4 population, and we have our CD8 population, and they're pulling out, okay? It looks like we don't have as many CD8s as we have CD4s in these lyophilized cells, but what we do see is we see the nice resolution of the populations, even though these two fluorochromes are traditionally something that you would not be able to look at on a conventional cytometer, okay? So we're able to see them. I'm going to go ahead and continue on recording and see if anyone has any questions on this specific data set as we're going along.
Yeah, there's a couple of questions here, Kathy, and maybe I'll start with the easier one. Do you save width? You can get area, height, and width in the same way we can normally, and do you save that?
Yes, so that is typically something I do at the beginning of an experiment. If you go to signal, you do have the capability to enable width at the very beginning of the experiment or before you start running. So I didn't set it up today. I was trying to save some time. I didn't go through exactly everything, but we did do that in the first session where we enabled width. But by default, forward scatter area and height is, and side scatter area height and side scatter blue area and height are always selected. But that is a good additional parameter to have open for singlet detection, always.
And obviously we're just doing two colors here. Yes. So there's another question is that live unmixing, is that just as easy if you've got more colors, or does it get harder the more colors you have? Is it slower? Any issues with the software or the hardware coping with that?
No, I've had no experience with it going slower. When you have a lot more in the way of fluorescent detectors, fluorochromes, not detectors, because the detectors remain the same no matter what. When you have more fluorochromes, what can wind up happening is that initial live unmixing, when you click on it, might take a little bit longer, but nothing too drastic. It doesn't take like a long period of time at all.
Yeah, well, I mean, once it calculates the unmixing matrix, then it's just a question of applying. I mean, it is higher, higher dimensionality, but still, it's something that it can cope relatively easy. So.
And Svetlana was asking the question as well about the area scaling factor and how much attention you pay to that. Again, presumably that's similar to what we would be doing in Flow. We check it for different cell types.
Exactly. So like I mentioned a little bit earlier, you might run into circumstances with very, very large cells where even if you bring the gain down to much lower values like 10 or 5, the signal might still be off scale when you're looking at forward scatter and side scatter area. In which case, you want to make sure that you go to the lasers tab here and adjust this area scaling factor, because you'll see a population that's much more skewed and potentially off, and you can reduce this forward scatter area scaling factor to help bring those cells on scale. But like I said, there is newer hardware for the Aurora that has come out to assist with that, because on our original unit that we had from quite a while ago, we were running into that a little bit more, but we don't really run into that as much anymore, even though we still train our users how to adjust the area scaling should you be working with very, very large cells.
Okay, thanks.
Perfect. Okay, so what we have for the rest of the run today is we do have some more examples, but this data has already been run. So these are all going to be with very cell leukocytes that have been stained and acquired on the same instrument. But for sake of time, so that we can go through all these examples, they're already loaded onto the instrument in other experiments. So I'm going to go ahead and I'm going to close out of this experiment now that we've seen that PAC blue and BB421 is a possible combination on mutually exclusive markers. And I'm not going to save the user settings, and I'm not going to make any changes to our default worksheets, but I will save the experiment, okay? So I'm going to go ahead and hit yes, save in case we want to come back to it later. And what I'm going to do is I'm going to open up a list of my experiments that I've previously run, okay? So the next thing that we want to go into is a PAC blue and BB421 when it's on co-expressed markers, okay? So if I double click on this experiment, you'll see that we already have data associated here. And we wanted to show an example, not just of CD4, CD8, right? We wanted to show an example where we would have CD3 and CD4, right? Because you'd expect there to be CD4, CD3 double positive. And can it resolve as well, right? These two fluorochromes are very similar. So what do we expect here? So whenever you see that there is this green tube that's filled up, the unmixing has been done. And whenever you see this little overlay of spectra, that also means the unmixing has been done. So the data has been recorded and the unmixing has been done. So in case I just missaid that or misspoke there, when the green tube is filled, that means data has been recorded. And in addition to that, the spectrum overlay that's next to it means it's unmixed, okay? So I'm going to jump straight to the CD3, CD4 sample that was co-stained, just so that we can take a look and see what it looks like on co-expressing cells, okay? So I double click on this P1 gate right here. And I figured we would go ahead and do the gating strategy together. So we're going to do something very similar. Forward scatter height and area. Create a polygon gate for our singlets. Drag our population hierarchy over. And then what I'm going to look at here is CD3, right? So we see our nice, beautiful CD3 population, but is it going to be able to resolve CD4 as well? And when we click on that, this is where I have the drum roll from either Rui or Derek. We see that it does pop up, right? Thank you. So this is an example here that we wanted to show in case people had a little bit of a doubt there as to whether or not this is a possible combination on markers that you know, are co-expressed. So we do see that you have your CD3 single positive, we have our CD4, CD3 double positive, and then you also have this dim CD4, which is likely some monocytes that are still in this scatter gate, right? So that is the example of how you can combine these fluorochromes without, or even though the markers are co-expressed. Okay. If we have any questions on that specifically, we can take it now, but the whole process was exactly the same here. We just had this data preloaded. And if there are no examples or questions rather, what I'm going to do is I'm going to go back here to the Cytek full spectrum viewer, because what we want to show next is an example of another combination of fluorochromes that are very similar. So the first thing I'm going to do is I'm going to get rid of my tags. The second thing that I'm going to do is I'm going to change back to my configuration, because I know that I'm not on a 5 laser unit. I'm on a 4 laser unit. I am on a 5 laser unit, okay? Now, the two fluorochromes that we're going to look at for our next run that we recorded a little bit earlier is Alexa 700. So if I type in Alexa, can't type in that little R, So I'm going to scroll down. We see the Alexa 700. I'm going to double click on that. Okay. And the next one is APC R700. Okay. When I double click on this one right here, you can see in comparison to the PAC Blue and BB421, which I could always bring back up if we need, the signature or the full spectrum signatures are similar, right? They're a little bit more similar than what we saw on the previous combination. And when I select similarity and complexity, what we see here is the value is much different. So we were about 0.77, 0.78 before, and now we're at 0.96, okay? Maria, are there any questions that popped up?
Yeah, actually, interesting questions, and especially to do exactly with this. So Laura is asking if the ability to resolve co-express markers on highly overlapping fluorophores also depends on the size of the panel. And, you know, basically, you know, if you have a larger panel with two overlapping dyes, would it be worse than if you had just a smaller panel?
Yeah, so once you start increasing complexity of the panels, it does just that, right? So once you start adding more and more fluorochromes, the complexity increases, and that is going to be compounding, right? So you do want to be very, very careful on how you approach these combinations. So my approach and the approach that we typically tend to take here is we ask everybody exactly what fluorochromes are, exactly which markers they're looking for, which are co-expressed, which are not. And then we look at reagent availability. As much as possible, we try and avoid these combinations that are very, very similar, but there are sometimes restrictions where you don't have certain reagents available to you. So this is saying it's possible, but as you start getting into more complex panel design, it might not be ideal.
Yeah. And I suppose it goes back again to it's not that dissimilar, is it, to traditional flow cytometry? We're getting photons from things that we don't want ending up in our detection channels.
Right.
Exactly. Exactly.
Right. Then the other question is, do the extra channels, oh, actually there's a question before, but do the extra channels facilitate unmixing for close fluors if they bleed into them? I can answer that. I mean, yes, absolutely. The more channels you have, they could be helpful. I mean, it doesn't mean they will, and especially if the peaks are low, they may not have, depending on the type of unmixing that it's done. But I believe with Cytek's linear unmixing, it doesn't take as much, you know, the weight of the lower peaks are not as high as the higher peaks, but still it could. It could facilitate, yeah. And then there's another question. What is the importance of setting the peak detection in your single controls? Could two fluorochromes that share peak fluorescence in one detector be separated in the rest of the spectrum, if the rest of the spectrum differs?
Yeah, so that's the beauty of full spectrum, right? So it's not just taking one detector into consideration and that one peak. It's looking at the full spectral signature, and that's the whole beauty of full spectrum technology, right? And us being able to utilize this, you're not just looking at one detector.
Right. And just a quick mention, so I don't know if that's what they mean. You know, when we set the peak channel, that's just for reference of the software to show when you're setting the gates for unmixing, it's going to show you the channel, the peak channel, but it doesn't influence the unmixing, right? You can actually change the peak channel and you know, just for visualization. It's not for the unmixing.
Yes. Okay.
Oh, and Agatha is asking, I'm not sure if you guys understand the question. She says, if you want to add new patient to experiment, we should create new experiment or add new tube. Okay. Oh, I think I understand. Okay. See where she's getting.
So it might be, say, for example, you might have a different tissue type, a different patient, right? There might be different types of samples that you're looking to run with the same panel. And if that's the question, what I will suggest to do, you can run different groups or like, you know, if the unstained autofluorescence is the same between these different patients or between these different groups, you could just add more tubes. If the panel's the same, but you have different tissue types or different patients that have drastically different autofluorescence, what you can do is you can add a group and you can set a group specific unmixing by selecting an unstained control that's specific to that group when you're doing the setup. So if we have time at the end of the run, I can go back and show that. But you have to be careful that you don't use the unstained autofluorescence from one type of cell that has a specific autofluorescence for your whole experiment if you do have different autofluorescences, if that's the question.
I believe it is, yeah. I understood it like that. Okay.
Okay. So let's go ahead and go back into the software then. Taking into account, we see that we do have a combination that's much of fluorochromes that has a much higher similarity index, right? 0.96. It's getting a lot closer to that value of 1. So we're going to go ahead and I'm going to close out of this experiment. I'm not going to save these changes. And we're going to take a look at the example of the Alexa 700 and APCR 700, which we have already run at this instrument. So again, for this experiment, I had ran the unstained, APCR 700 single color, Alexa 700 single color, right? So if I look at all of these, we already had these samples run, okay? And then what I can do is I can look at the fully stained for this sample to see what it looks like, okay? Now here, because it's a combination of CD4 and CD14, I'm going to set this scatter gate to include this population of monocytes right here before proceeding, okay? So I'm not gonna focus just on my lymphocytes here anymore. We're looking at the whole population of cells. We'll look at our singlet gate. I'm going to set a polygon, again, for our singlets, okay? And if I double click here, let's look now to see what it looks like for a combination that has a much higher similarity. So here we'll look at APCR 700 for our CD4. And here we're going to look at our CD14. So it's already looking a bit different. It doesn't look as clean, but I also want to take into account the fact that my scaling is not great here. So if you're looking at the plot properties here on the right, we're on our manual scaling here for by exponential, and you do have the capability to make changes here. So if I change this to negative 7,500 as opposed to 1,000, negative 1,000, that looks much different, okay? I can do the same here, or alternatively, I can change it to auto scaling, right? So you can do either auto scaling or manual scaling when you're looking at by exponential in the software. Okay? Now, if we look at this data, what we can see is it does not look as clean, okay? Now, we have this population that's coming up here, right, for the unstained. We see this population that's just kind of veering off over here. And the point of us showing this is that not all combinations are going to be ideal and not something that we would necessarily suggest, okay? So you can see the difference there between PAC Blue and BB421 and APCR 700 and Alexa 700. This is one circumstance. So this is just a trial that we ran at the instrument to test it out. But you can see that that data is definitely not a great example of what you would want to see if you were analyzing your flow cytometry experiment, okay? Now, with that, the next thing that we're going to try and do somewhat briefly is go over autofluorescence extraction, okay? We just wanted to show this, this example, and with that, I'm going to pop it back to Rui.
Okay, thank you, Kathy. Okay, yeah, so we're running a bit late. There's a question from Jim. We were taught those lines are unmixing errors and should be gated out. I mean, it's important if there are unmixing errors you should address why are there unmixing errors and try to correct them, right? Rather than gating them out. So no, I wouldn't gate them out. Is it possible that two differences, Cedric is asking, is it possible that two different strength of two antigens may cause this? Kathy, you want to answer that?
So I don't necessarily think that it's because of the antigen expression or how high it's expressed. I do strongly believe that this is related to the similarity of these two fluorochromes and the similarity index there, which is why it's more difficult for this to carry out the unmixing. And I would avoid this combination with these two markers, and I wouldn't put them together. That would be my suggestion here, as opposed to taking into account antigen expression.
And Laura's actually asking something very interesting. She's saying that those unmixing errors look like more autofluorescent issues, and maybe not necessarily to do with the fluorophores. I mean, we did put fluorophores that are very similar, so they're probably very related to that, but she's right. And actually that's a good segue to what we're going to talk about, you know, where we can play around with actually including autofluorescence as a separate channel, or separate fluorochrome, let's say, or including it in each fluorochrome. Okay, I don't know, while I'm switching, if you want to answer the questions that are here.
Well, I'm not sure I can answer it, but it's something we were discussing the other day, isn't it? If you've got a heterogeneous population and you have different levels of autofluorescence, how does the unmixing algorithm actually cope with that? I'm not sure I could answer that question.
Okay, so I'll let Rui kind of try and tackle that as he's getting his slides up. But one thing that, oh, sorry, go ahead.
Yeah, no, so it's from Jim. Is it the question from Jim?
About the heterogeneous population or heterogeneous populations and autofluorescence and how it accounts for that. So that was the question that that I think popped up.
Oh, two different levels of autofluorescence. Yeah, so I mean, right. So I was a bit lost with the question here, but yeah, if the two signatures are different, you know, we should consider them as two different fluorochromes, right? If again, many times, since autofluorescence is basically usually a composite of similar fluorochromes that cells have, right? Natural fluorochromes like NADPH and flavonoids and things like that. So the idea here is that if the signature is different enough, then we need to address that, right? If they're very similar, you probably can get away with one signature as long as the signal of the autofluorescence is not too high, right? So there are several things to play around. You know, to be honest, we haven't really played too much around with different autofluorescence because most of the times the autofluorescence is low enough not to really pose much of an issue, right? But again, like Kathy was saying, if you have different tissues, yeah, we definitely want to make sure that we account for different autofluorescent signatures, right?
I suppose, Drew, if we do your slides, hopefully things might seem a little bit easier to people,
okay,
or it'll bring up more questions. We'll see.
Right, exactly. Okay, so I'll go ahead. Let me just remove the Q&A from. Oops, I need to remove these. Okay, so yeah, so the second point we wanted to address here, and we'll try to do it very quickly. I was so proud to have just a few slides to show, and I could do them calmly, but I'll have to. Do this in somewhat of a rush. So let me just remind you of how, you know, conceptually what spectral unmixing is doing. So, you know, think of when the cell goes through the laser, basically there's going to be signal in all of the channels, right? So you're going to end up with, let's say, a total signature, which is the sum of all of the individual signatures of the fluorochromes that are represented in that cell, right? So the whole point of unmixing is trying to quantify the abundances, the quantity of each fluorochrome that exists in the cell. So basically, the first thing you need to do is to tell the instrument what are the fluorochromes that are there. So, you know, let's say we have, we've stained them with FITC and PE. So we would have two signatures that we would have to provide, but again, with full spectrum flow cytometry, we need to also think of the not only the fluorochromes that we're adding, but also the fluorochromes that already exist naturally in the cells, which is the autofluorescence. So we need to provide also the autofluorescent signature. Sometimes that autofluorescent signature is very low, as we were discussing, and so it may not really have an impact if you don't use the correct signature. But of course, you want to make sure that you're using the signature, as correctly as possible, right? So, instead of thinking of, I've added 2 colors or a panel of 20 colors, it's always a panel of X amount of colors plus autofluorescence, right? And so what the unmixing does is basically quantify the abundances. So in this case, you have a certain amount of FITC, a certain amount of FITC, a certain amount of PE, and a certain amount of autofluorescence that altogether, summing these signatures will give you the total signature that's drawn here in blue, right? And so the instrument then knows how much of each fluorochrome the cell has, and it will plot it accordingly, like we're used to seeing in a flow cytometry plot. And then the second cell goes by, and you again, in this case, it determines that it has half of the PE fluorescence, and so it will plot it accordingly, and you have the same amount of FITC, but half of the PE fluorescence. Now, if the algorithm is basically unmixing using autofluorescence as an extra fluorochrome, then what happens is that what we're seeing here as the amount of FITC and as the amount of PE is the true signal of FITC and PE without the autofluorescence, right? Because normally in a classical flow cytometer, when we're looking at FITC, we're looking at FITC plus autofluorescence, right? We're looking at PE plus autofluorescence. So we're not able to extract that autofluorescence from our data and from each channel. So again, with full spectrum flow cytometry, we can do that. And the advantage is that can give you, in some cases, amazing results. Like, I like to show again in images where you can see here, for instance, this image here, where, it would be very difficult with classical imaging, fluorescent imaging, to be able to distinguish between autofluorescence and the real fluorescence of the cell. And by extracting autofluorescence using linear mixing, just like the Aurora does, you can see that all of the autofluorescence has been dropped down almost to 0. And then all you're left with is the real fluorescent signature and fluorescent signal. The same thing here, you can see that, this is already pretty good image, but by removing autofluorescence, it becomes very clear what exactly is GFP and what is not, right? And what is the autofluorescence. And if we think of, or if we go to an example, using the Aurora, this is just one of the cases where I believe this was an experiment with prime flow, where usually cells end up having a very high autofluorescence, and without autofluorescence extraction, where alexafluor88 in this case we're adding the autofluorescence in this channel, so it's alexafluor88 plus autofluorescence. As you can see, it's very difficult to distinguish and to separate these two populations. Once we extract autofluorescence, sorry guys, I'm pressing the wrong button. When we extract autofluorescence, what ends up happening is that now we're just seeing alexafluor488 in the alexafluor88 channel, and the autofluorescence should be equal to 0 because we've extracted the autofluorescence completely from this fluorochrome. And so I don't know if we still have time, but Kathy was going to show you very briefly the advantages. Not only sometimes you can pull apart because you can subtract the autofluorescence from the fluorescent signals, but also sometimes, as a few of you were discussing, sometimes we're able actually to improve the unmixing because, again, you're providing more information. And if the autofluorescence is relevant enough, significant enough, that can have an impact.
So the good thing is we absolutely have time, because the beautiful thing is it's nice and easy to do in the Aurora. So I'm going to go ahead and I'm going to share the screen again. But it absolutely is something we'll be able to cover. And there was one question in the Q&A that we should have time for as well. So we already covered in setting up the experiment how we go ahead and do the unmixing. So what I'm going to do, right, we have this experiment set up here, and there is one quick thing. So actually what I'm going to do first, I have to create a new experiment and import these raw files in just to show very quickly. Okay. So what I'm actually going to do is I'm going to hit, go into another experiment, right? So we did our test a little bit before where we created our CD4, CD8. And what winds up happening is when you create your experiment, when you select unmix, I'm doing this to save a little bit of time. The only thing that you have to do here in order to reduce the impact of autofluorescence and do the autofluorescence extraction is click this button in the bottom left corner. So here I'm showing you with this BB421 pack blue for CD4, CD8, but what the example I'm going to show you as far as the actual results is going to be with CD3 and CD56, right? But all you have to do in the software with Spectral Flow in and of itself is check off the autofluorescence as a fluorescence tag. And when we hit next, everything remains the same in this unmixing window. You set the scatter gate where you would like it and around the population you would like. If you were going ahead and analyzing all of these cells, you would make sure that this P1 gate was around the full population, okay? But because we would just be looking at our lymphocytes, we would focus on this. And then we would do live unmixing if we still had samples to record, or if we weren't live recording samples and wanted to look at it after the fact, we would do unmix, save, and open, okay? So that is really all you have to do in the software to look at the autofluorescence extraction. But I do have the results here in PowerPoint. So if we go ahead and take a look, this is the results of looking at CD3 and CD56 without and with autofluorescence extraction, okay? So I showed you how to do it in the software by just checking that button when you do unmixing. But what you see here in a CD3 and CD56 combination when we're gating on just this lymphocyte population is the negative population here that we're seeing is a bit skewed, and visually it's a little bit hard to kind of set some gates, and it might not be the best representation of the data when we're looking at the negative, okay? Once you look at the autofluorescence extraction by checking that box and calculating the unmixing in that way, this is the same exact data file with the autofluorescence extraction. So we know it's quick, but we just wanted to show the how easy it is to go ahead and utilize that function in the software and how it can actually compare when you're looking at the same data file with and without autofluorescent extraction, especially on like a combination that we know has a high similarity index with pack blue and BB421.
Right.
So it was quick, but that is
Very
our
good.
example for today.
Yeah, and I should say that you know, if you think of it, using always the autofluorescence as you know, as a fluorochrome should be the way to go, right? It makes sense because you're providing more information and hopefully the correct information to be able to mix correctly. There are two issues. One of them, maybe you don't have the possibility to, you know, because you have a heterogeneous sample, so you don't have the possibility to gate the exact autofluorescence of the cells that you're trying to unmix. But also, you know, there have been cases where using the autofluorescence extraction doesn't give you the best result. And this has been reported by Cytek. But, you know, unfortunately, we don't know from Cytek what is the algorithm exactly doing. So, you know, for the point of view of a scientist, it becomes difficult to make a choice whether you should use autofluorescence extraction or not. So the bottom line is you need to, you know, if you're seeing that your data has some problems with unmixing, then maybe try both and see if that improves doing the autofluorescence extraction. That's basically what we would recommend, right? There's also another question here. Do you recommend not to adjust compensation values if analyzing in FlowJo to correct this unmixing issue? No, the only way to correct unmixing issues is to either unmix properly or go back and correct the controls. Manipulating the data afterwards should be considered fraud. So this is my point of view, at least.
Yes, and I very much agree with that. I'm masked now as we're running a little bit late, so we have people joining the lab. But that is something that I would never recommend under any circumstances, because especially with this full spectrum data, right? As you're trying to try and look at it and make any corrections, you don't know the impacts that you're having on your full panel.
Right.
And the other thing is when you load it into FlowJo, you honestly can't make changes, right? You do have the ability to do unmixing with FlowJo and with FCS Express and with third-party software, but you can't modify this, like these results as they come through, to my understanding. So you couldn't do it anyway unless you redid the unmixing as a complete.
Right. Oh, there are interesting questions here. Laura says that from the last year's Aurora user group meeting, low autofluorescence, when you have low autofluorescence, you shouldn't use this feature, and you should only use it when it's high. I mean, personally, I'm not happy with that, just, you know, that explanation. Again, since we don't know what the algorithm is doing, you know, you're basically trusting what the company is telling you. And also, it's not very obvious and objective what low means, right? I know they mentioned 10 to the 3, but, you know, to be honest, you could change the settings in such a way that you don't have the autofluorescence at 10 to the 3, you have them somewhere else. And, you know, are you still going to use autofluorescence extraction or not? So for me, at least, it doesn't seem a very convincing explanation. And it does worry me a little bit that this has been addressed so loosely, and we don't really know what is going on.
Yeah. Yeah, I mean, at the end of the day, it's a really wonderful tool that we can use, but you have to look and see whether or not it benefits your experiment.
Yeah.
And do the comparison, just like we'd say for beads and cells, right? You have to test it and see for your specific applications. But
right.
There's definitely more to learn there.
Right.
Yeah.
Yeah. The other question is by Cedric. He's asking, subtracting the autofluorescence, it seems that we do not decrease any original signal. Is that true? No, I think you do decrease the original signal. It's just that it's not a very obvious, because we're looking at a log scale. So if you subtract, let's say, 1,000 to 10,000, you know, maybe you'll see just a slight shift, which is not very obvious, but you'll see it, of course, if you subtract 1,000 to 1,000, it becomes 0, right? So it goes 3 logs below. So you're going to see more of an impact to the, you know, with the lower signals, but it does subtract to everything, right?
Yeah. It looks like there also might be another question about re-unmixing. So I said recompensate, but re-unmixing the data to get a better result. Theoretically, if you run it through, if you see something that looks way off, no matter what algorithm you use, that I believe that would still be there. So what I would always suggest to do to get better results is have better controls and try and identify what's going on with the controls. And oftentimes by doing some sleuth work, you can really identify, you know, where you might have the issues in the controls themselves.
So the data that comes out of the Aurora, then that's the unmixed data, isn't it? It's not like the raw data.
Well, you get both.
No, you do. Right.
Yeah. So if we look
so you
here,
could run that raw data through a different algorithm.
Exactly.
Yes. Yes.
So the file path that we have here, right? If we look today, we're in the admin account, and we did this test run. We get a raw output and unmixed for every FCS file from each group. Yeah. So you have both of those folders that will pop up for raw and unmixed.
Right. And I think Desiree's question is has to do with the fact that, yes, I think both Cytek but other people have recommended recompensating the data. So running compensation over the unmixed data. You know, honestly, you know, I don't have a way to, you know, to prove that that wouldn't be correct, but you know, unmixing should do a pretty good job. If it's not doing a good job, is again because of limitations of the data, the controls, maybe the panel that was designed is just not a very good panel. So you know, I don't personally. I find it it's just like if you had compensated data and it didn't look good, you would recompensate it. You know, it's the same thing because again, compensation is just a particular case of unmixing. So you're running twice, and then you could ask, well, after recompensating, does it still look good? No, let's continue compensating until it looks good. So the problem here is that we're trying to look visually, you know, if things make sense or not. And I think that's very dangerous. You know, if we see that something doesn't look good, we should go back to the controls and to the data and try to improve whatever we have, not to recompensate.
Okay, and there's another question, I suppose, practical question about how do you create an autofluorescence channel to do the subtraction? So that's just a question of just running the unstained cells, right?
Yeah, so when you do the unmixing, there's an option that says autofluorescence as a fluorescence tag, right? So that's what we showed earlier. But when you click, if you have the autofluorescence extraction done, there's this AF-A that pops up, the autofluorescence, right?
Yeah.
That you don't have pop up.
You know, right. Here I want to, yeah, I want to just emphasize the fact that the algorithm is not subtracting, right? It's not subtracting autofluorescence. It's calculating the amount of autofluorescence, right? That the cell has, right? So it's calculating the abundance. To be honest, again, since I don't know the details of the unmixing algorithm, I don't know what it does when it's not doing the autofluorescence extraction, but maybe the term autofluorescence extraction is not the happiest one, because it does give the feeling that it's subtracting. It's not, it's just calculating. So here's my take. I think that without autofluorescence extraction, if you have 10 colors, it's just using the 10 signatures to do the unmixing. And so every abundance that it's calculating of those 10 fluorochromes will include the abundance of that fluorochrome plus autofluorescence. If you click the box autofluorescence extraction, what it does, it unmixes with the 10 signatures plus the autofluorescence signature. And so it calculates directly the amount of autofluorescence, meaning that all the other 10 fluorochromes will not have any autofluorescence signal added to it. So I think that's I think that's an important distinction. It's not subtracting autofluorescence from anything.
That's a good point. And that terminology is very prevalent. And I myself have to check myself on it, because it's so easy to fall into that pattern of saying that that's not what's happening. Yeah.
Right.
All right.
Okay, so nice. Now, Laura is saying that Cytek did add more about how the autofluorescence extraction works on their on-site training. Yeah, absolutely. That would be nice to know more about, and we're looking forward to it. So that's a good point. Maybe we could add that to the comments when we publish the video. Maybe we could put some information on that there.
Sounds good.
I'll make a note.
Okay, thank you. Thanks, Laura.
Okay, so we have run over time a little bit, haven't we? So we should probably just wrap this up. Rui, I think you've got a couple of last slides just so we can mention to people. So as Kathy mentioned earlier, all of these videos will end up on the OpenFlow Cytometry YouTube site, which we have a link to, I think, in one of these slides. Or if you can't find it, you should be able to search OpenFlow Cytometry anyway. And this will go up probably mid next week. We, as I said at the beginning, we hope to run these monthly. So we will be back again on the 12th of February, same time, same place, when we're going to look at cell sorting. This was one of the things that came up when we sent around a questionnaire at the beginning of these webinars. And we're going to look at the theory and some practical considerations. First of all, in the first session, we'll probably spread over 2 sessions using the Sony SH800, which is one of the more user-friendly machines on the market. And if you want to register for that, registration is already open on the Crick What's On page. You can see the URL there. If you don't get time to get it down, you can always email myself or Rui or Kathy. We'll send you the details, or follow us on Twitter as well. Both of us will be putting those details up, Twitter and LinkedIn. So you should be able to get that information from us somewhere.
Yep.
Okay, so thanks everybody for coming, especially for sticking around a little bit later than we anticipated. And we hope to see you all again in 4 weeks' time.
Thanks, everybody. Thanks for some great
Bye,
questions.
everyone.